Angkor is often described as the ceremonial climax of Khmer civilization, a final expression of power, faith, and artistic achievement. This account starts from a different premise. Angkor functioned as a large-scale environmental conditioning system, applying chemical processes to land, water, and air in ways closely analogous to modern industrial practice. The system was powered by the environment itself. Seasonal monsoon storms crossing the Angkor Plain delivered not only water but energy. Electrical charge accumulated in saturated, iron-rich laterite soils. Laterite, rich in iron oxides, responds strongly to moisture, heat, and electrical stress during storms. This energy was not wasted, it was routed. Canals, causeways, stone foundations, and reservoirs acted as conductive and buffering pathways, guiding charged electric energy through the landscape. Energy discharged from monsoon systems moved into soil, stone, and water, where it could be absorbed, moderated, and applied. Long before the construction of Angkor Wat, the Khmer already understood how to manage soil and water chemistry at a local scale. Early temples, small reservoirs, and village systems were used to neutralize acidic soils, stabilize water, and create fertile ground for rice cultivation. These solutions worked when populations were small and environmental impacts remained localized. Between the 9th and 12th centuries, Angkor expanded into one of the largest pre-modern urban landscapes on Earth. More than 1,000 square kilometers of canals, fields, reservoirs, quarries, and stone complexes became a single integrated system. Centuries of rice intensification, deforestation, canal construction, laterite quarrying, lime burning, and stone building progressively altered soil and water chemistry across the entire plain. What had once been manageable locally became a system-wide problem. The water cycle began in the uplands. During the monsoon, rain moved through iron-rich laterite soils, absorbing heat, electrical charge, acidity, and suspended sediment. This water entered canals already chemically and energetically loaded. Canals did not simply move water, they regulated velocity, direction, and timing, routing flow towards central basins designed to absorb both material and energy. The Great Barays functioned as thermal, electrical, and chemical buffers. They slowed movement, released stored heat and charge, allowed sediment to settle, and equalized volume and chemistry before redistribution. Angkor Wat appears late in this sequence because it scaled up knowledge the Khmer already possessed. Its layout mirrors a modern lime production and water conditioning facility. The vast moat functioned as a primary settling, dilution, and energy dissipation basin. Incoming water was slowed, spread, and stabilized before entering the core. Internal pools, including the so-called library pools, operated as slaking and mixing tanks where lime could be hydrated and evenly dispersed. Long galleries and courtyards regulated flow paths and residence time, functioning much like clarifiers in contemporary treatment plants. Sandstone and laterite surfaces were not passive. They provided chemically and electrically active contact areas that buffered pH, moderated reactions, and dissipated charge as water moved through the complex. Controlled outlets released conditioned water gradually, preventing chemical, thermal, and mechanical shock downstream. From here, stabilized water was distributed outward to rice fields, maintaining fertility across the plain. Excess water, sediment, and waste were discharged downstream, preventing accumulation and system poisoning. Barays buffered heat, charge, and chemistry, Causeways regulated distribution and load. Temples functioned as durable processing nodes embedded within a managed hydraulic and energetic circuit, but the system extended beyond water alone. Angkor was designed to condition land and air through chemical processes driven by environmental energy. Electrically active stone, constant moisture, and moving water sustained electrochemical gradients across the system. These conditions drove reactions equivalent to electrolysis, separating water into hydrogen and oxygen. Hydrogen dispersed upward as a reactive reducing agent. Oxygen enhanced oxidation and purification within enclosed and semi-enclosed spaces. Large domed towers functioned as containment and venting structures, stabilizing and releasing outputs in the same way industrial reactors do today. In this reading, Angkor was not a symbolic endpoint. It was an engineered response to centuries of environmental and chemical stress, a city built not to celebrate success, but to keep an empire alive. In 1431, that system was violently interrupted when Angkor was sacked by the Siamese forces of Ayutthaya. Maintenance ceased. The hydraulic network was abandoned. The conditioning system went offline.